Today, what I wanted to do is basically kind of go through the basics of how fully homomorphic encryption works. So, fully homomorphic encryption, and as I'll get into a bit later, basically is this kind of encryption that allows you to run computations on encrypted values, right? And there's a lot of things that are really interesting about this. Like you can do privacy preserving computation really easily. It's also an important building block in some multi-party computation protocols. It's an important building block in a lot of the proposed obfuscation protocols that people are starting to come up with. And the interesting thing with fully homomorphic encryption is that like it sounds scary. Like there's a lot of I feel kind of impressions that it's this very complex form of cryptography. It just got figured out only slightly a couple of years ago, and so it must be really complicated to understand. And it turns out it's completely not. Like it turns out that fully homomorphic encryption protocols are literally kind of simpler to fully understand, I would say, than even a lot of elliptic curve based constructions. Uh, Now, the reason we're not using fully homomorphic encryption for everything is basically because it's not very efficient, right? And it has high overhead, it has ciphertexts that are very large, and I'll get into why this is the case fairly soon as well. So to start off, let's talk about kind of what is fully homomorphic encryption, right? So the goal of fully homomorphic encryption is basically to have an encryption scheme where you can compute on encrypted data, right? So if you have an encryption of X, you want to be able to turn that into an encryption of f of X for some function f, without being able to decrypt, so without being able to determine X or determine f of X. So you can think of kind of partially homomorphic encryption protocols that we know about already. So if you think about even elliptic curve points, now this doesn't technically fully satisfy the definition of fully homomorphic encryption because it's not it's not an encryption scheme. It's just a group that has a homomorphism. But if you look at elliptic curve points, if you take some number x and you multiply it by some elliptic curve point that's the generator, and then you add the generator multiplied by y, you get the generator multiplied by x plus y. This is a really nice property of elliptic curve points, basically that they do kind of follow this and distributed property, right? And there's a lot of protocols that do make use of this, right? So in the case of blockchains, for example, there is deterministic wallets that have master public keys that they rely on these elliptic curve homomorphisms. There's even zero knowledge proof protocols and based on elliptic curves, things like bullet proofs, even just signatures rely on this kind of additive homomorphism. So it already provides a lot of value, right? And if instead of adding you want to be able to multiply, then you can just use RSA, right? If you just use kind of simple RSA encryption, so x to the power of e, then xy to the power of e equals x to the power of e times y to the power of e. And so if you have the ciphertext for x and the ciphertext for y, you can create the ciphertext for xy, right? So we have this kind of family of schemes that gives us additive homomorphism, and we have this family of schemes that gives us a multiplicative homomorphism. Now the question is, can we come up with a scheme that lets us do both, right? So can we come up with some way of making a ciphertext so that you can do both adding and multiplying on ciphertexts? And if you can add and multiply, then you basically have general purpose computation, right? If you restrict your ciphertext to just being zeros and ones, then you can do pretty much every logic gate, right? So if you want to do and, then and of x and y is just x times y. If you want to do or, then, well, or is basically you can kind of invert x, invert y, then you do an and, and you invert again, or you have this kind of simpler formula where you just say x plus y minus x times y, right? So if both value inputs are zero, then this is obviously zero. If x is one, then you have a one here, you have a zero here, and then you subtract a zero here, so you get one. If y is one and x is zero, it's symmetric, so you also get a one. And then if x and y are both one, then you get 1 plus 1 minus 1, so you also get 1. For XOR, you can do either just x plus y, and that's if you don't care about the numbers staying within kind of the range 0 and 1, if you just care about them being even and odd. Or if you care about the numbers being within the range 0 and 1, then you can just do x plus y minus 2 times x times y, right? So if x and y are both 1, then it's 1 plus 1 minus 2, and you get to 0. So if you can add and multiply, then you can do pretty much whatever logic gates you want, and you can do arbitrary computation. Now, it's not going to be efficient arbitrary computation, because if you imagine wanting to do some math based off of numbers, then you'll pretty much have to decompose those numbers into bits, and then you'll have to turn your addition and your other operations into circuits, and then you have to evaluate the circuits, and so you can see how kind of the complexity multiplies, but you can do it. So to give the intuition around how these FHE protocols work, we'll start with a kind of toy protocol. And this is, I believe, technically secure under some kind of very, very unfavorable key sizes and complexity. But like, this is the way that people started kind of figuring out how to be able to do addition and multiplication, right? So imagine your private key is a big prime, and think of it as like a really big prime number. Then to encrypt a message where a message is restricted to either 0 or 1, then what you do is basically you take a big random number, then you multiply it by p, then you add together a small random number multiplied by 2, and you add your message, right? So what we have here is basically have a multiple of p that's offset by some noise and a message that's hidden in the least significant bit of the noise. And if you want to decrypt, then you decrypt the ciphertext with the key by basically saying it's the ciphertext mod p in brackets, and that kind of kicks out this term, and then you just do mod 2, and that kicks out this term, and so you have your m left. By the way, if people have questions at any point, please feel free to ask. I'm happy to answer. So why is this scheme additively homomorphic, right? So why is this kind of approach where you encrypt a message by taking a big multiple of your key, adding some noise, and then hitting your message in the least significant bit of the noise? Why is this additively homomorphic? Well, basically, if you imagine you have two ciphertexts, each one of these ciphertexts is going to be a multiple of p plus some noise plus a message, multiple of p plus some noise plus a message, and these things just kind of naturally distribute, right? So basically, the CT1 plus CT2 actually is a ciphertext. Like, it's a ciphertext in the correct format because you just have a multiple of p, that is k1 plus k2. Then you have your noise, and the even part of the noise it also adds up. So you have 2R1 and 2R2 over here, and then it's just 2 of R1 plus R2. And then your messages add up, right? So M1 and M2, basically you have M1 plus M2 over here. And note that this is addition mod 2, right? So if your message here is 1 and your message here is 1, then this is 2, but the 2 over here is indistinguishable from just being part of the noise, and so it just becomes the same as 0. But if we just want to do binary circuits, then this is totally fine, right? So you can add together two ciphertexts, and you get a ciphertext that is of the correct format of the addition, or rather of the XOR of the message bits. Now, why is this multiplicatively homomorphic? So let's say you multiply together your two ciphertexts. Then you have an expression of the form that your first ciphertext, k1p plus 2r1 plus m1, multiplied by your second ciphertext, k2p plus 2r2 plus m2. And you basically just kind of fully expand this. And when we expand it, we're just going to say, like, first of all, let's figure out which terms are multiples of p, right? Because if you remember the decryption process starts off by just modding, which just kills all your multiples of p. So let's figure out what the multiples of p are, because we don't have to care about them. Basically, you have k1p multiplied by all three of these. Then you have k2p multiplied by all three of these. So these 5 terms go over here. Now you have 2 times So now we have to figure out which of the remaining terms that are not multiples of p are even, and it's basically 2r1 multiplied by this, and you have 2r2 multiplied by this. So you have a bunch of terms that get multiplied by 2, and then you have this thing over here, which is not multiplied by p and not multiplied by 2, which is just the product of the messages, right? So if you take this expression and then you do a mod p and then you do a mod 2, then the mod p is going to kill these 5 terms, the mod 2 is going to kill these 3 terms, and so you just have this one term left. So we see that this is additively homomorphic, we see that this is multiplicatively homomorphic. Now, why does it have kind of any level of security? Basically, it's this approximate GCD problem, right? Basically, if you did not have noise, so if we did not have this kind of 2 times small random, then you have just a bunch of multiples of p plus 0 or 1, and then a bunch of them are going to be just multiples of p plus 0. Then you can just use any GCD algorithm, and then you just keep just the Euclidean algorithm, and you just GCD all of these multiples together, and you get p, and then you can kind of break the scheme, right? But as it turns out, if you just have approximate multiples, then figuring out what p is becomes much harder, right? So the security of this cryptographic scheme is based on kind of the hardness of computing approximate GCDs as opposed to computing kind of exact GCDs, which is easy. So there's a more general principle here, which is basically that solving systems of equations becomes much more difficult when these equations have errors, or you can call them noise, right? So if you add some noise into your equations, then suddenly figuring out kind of parameters that are parts of those equations that you can normally figure out easily, it just suddenly becomes much harder. And this is pretty much what kind of the security of all of these constructions ends up being based on. So as a side note, public key encryption. So I showed this scheme as being a secret key scheme, right? You need P to encrypt. Now, turning these schemes into public key schemes is really easy, right? You basically just provide a bunch of encryptions of 0, and then if you can public key encrypt 0 by just computing a random linear combination of these, and you can add some more error. And if you want to encrypt 1, then you could just take these encryptions of 0 and add 1. If you want something more generic, then into your public key, you can add some encryptions of 1, and then to encrypt 1, you add a bunch of encryptions of 0, and then an odd number of encryptions of 1, and you have a new encryption of 1, right? So turning any fully or kind of homomorphic scheme that is private key, you can turn it into a public key one pretty easily. That's not a problem. Now, why doesn't this work already, right? So there's 2 problems. One of them is that multiplication just doubles the length of the ciphertext, right? So here you had K1P and K2P, and here you have K1, K2P. And actually, it's K1, K2P times P, so it's K1, K2P squared. And so the bit length of this multiplication is just going to be the sum of the bit lengths of the ciphertexts that are coming in. And so if you try to do more than a couple of multiplications, it just blows up horribly, and it just becomes impractical, right? So you can't do more than a logarithmic number of multiplications, period. But there's another problem, which is overflow of the errors, right? So if you remember, the sum of the ciphertexts kind of turns into a new ciphertext of this format, then the product of the ciphertext turns into a new ciphertext of this format. We can look at what happens to the even kind of error term here, right? When you add, the error roughly doubles. You take the sum of the errors. When you multiply, the error squares, right? So when you had R1 and R2, here you have a 2R1, R2. And so the bit length of the error doubles. And so once again, the maximum multiplicative depth is going to be the logarithm of the number of bits in P, so, or the log of P, right? So you can think of the maximum multiplicative depth as being really low. Like, think of it as being something like 10 or even 5. Like, it's tiny. So how do we overcome this overflow problem? So there's 2 general categories of solutions to this, right? The first category of solutions basically is that we do clever tricks to make multiplying only increase the error by a constant factor, And so instead of having log log p or log of the number of bits of p multiplicative depth, you actually do have a log p multiplicative depth. So the multiplicative depth is proportional to the number of bits in p, right? So if you imagine, we can make a protocol where every multiplication increases the error by some fixed factor, say a factor of 1,000, then that's only 10 bits. And so if your p has, or if your modulus has a bit length of, say, 10,000, then your multiplicative depth goes up to 1,000, which is already huge. Now, so this is one solution. And the second kind of solution is bootstrapping, right? So bootstrapping basically is this kind of key switching mechanism where what we're going to do is basically imagine that you have some ciphertext that has some noise, and you want to convert it into a fresh ciphertext that has less noise, right? So what we'll do is we will basically take the kind of circuit that represents decrypting X under some secret key, and we're going to evaluate it homomorphically, right? So what we're going to do is we're going to take X, so X is a ciphertext, then we're going to represent X as a bunch of bits, and what you're going to do is we're going to provide a kind of bootstrapping key. So think of this as being part of the public key of the system, where so first of all, you can encrypt the bits of X under some U key. So you can encrypt the bits of X here under some U key S2, but also we provide the bits of S under a key S2, right? So what this basically means is that you have, for some key S2, you have the regular public key for S2, and you also have an encryption of S under S2. And so given the value of X in the clear, you convert that into its bits, then you convert that into encryptions of the bits of X, and then you have encryptions of the bits of X, you have encryptions of the bits of S, and you just compute FS homomorphically. Basically, you just compute this decryption process using these inputs that we have. And what this gives you is this: the decryption process returns 1 bit, and so you get 1 bit, which is the decryption of X. So it is the same bit that X represents, except it gets encrypted under the key S2, right? So before we had a X, which is an encryption of some bit under S, and now we have basically an encryption of X that's under the key S2. So, and the important thing is, right, that X might have had a lot of error, but this decryption, it's only going to have a fixed amount of error, regardless of how much error you have over here, right? And the reason basically is that, well, from the kind of perspective of looking this under key S2, all of these bits start off as being a ciphertext of error of kind of the minimum error level. They start being kind of depth 1, and then this decryption has some constant depth, and so the amount of error that's going to be in the result is actually going to be constant, even if there is a lot of error in the ciphertext here. So before I kind of continue, maybe I should offer an opportunity for some questions, because bootstrapping is kind of a little bit complicated to understand. So maybe just kind of think for a bit and make sure that you understand what's going on here.
One question I have regarding bootstrapping is there randomness involved, and where does it come from?
Mm-hmm. So bootstrapping just basically means that you're evaluating the decryption circuit. So the place where there is a kind of error involved is basically that the process of homomorphically encrypting these X bits is going to involve basically taking values from the public key, and those values already have some noise inside of them. So the process of executing the circuit kind of after you have those values doesn't require you to have to add any extra randomness, but the bootstrapping key already has a kind of randomness that got used in the process of constructing it.
Right, that makes sense.
Could you describe what exactly? Sorry, I'm having. What's the output of the decryption function? What does that look like when it's evaluated in the circuit?
Right. So the output of the decryption function is either the bit 0 or the bit 1, depending on what the ciphertext X represents.
Right, but okay, so the thing I'm having trouble with is that I don't want the one evaluating the circuit to actually see those bits, right?
Correct.
So I don't
Okay,
want
so the
them to get the
reason why the person evaluating the circuit cannot see those bits is because that person does not have X, right? So computing the decryption requires you to have X, and it requires you to have X. Now, in your bootstrapping key, you're not going to give them X. You're going to give them an encryption of the bits of S under S2. And so the only thing they can do is they can evaluate the decryption circuit in a way that gives them just outputs that are encrypted under the key S2. They have no way of kind of extracting outputs in the clear.
I see. So DEC, they don't actually get DEC, they get the decryption circuit. Okay, they have some representation of it. They get the bits of S encrypted using S2. And they run this circuit using those bits.
Exactly. So they have S encrypted under S2. They have X in the clear, and so they just encrypt X under S2. And then DEC is just a circuit, and it's part of the algorithm, so everyone has it, and so you just evaluate DEC homomorphically using bits encrypted under S2, and so you get 0 or 1 encrypted under S2.
Right. So what you wrote below this enc DEC, that's not actually something I have to do. I only have to run the DEC, and that automatically already gives me the encryption. Okay.
Exactly. So this is just what it's equivalent to.
Yeah.
Right. Okay.
So what is K?
K is just whatever the value is that Z is encrypting.
Oh, I see. Thank you.
Once you've re-encrypted this, why can't you back propagate the new lower entropy or the new re-encrypted format with the lower error? Why can't you back propagate that lower error and gain a log factor or constant to give you your multiplication trick through every previous multiplication again?
How would you back propagate the lower error?
I don't know. I haven't tried to play with this yet, but
right. So
intuitively, it feels like there may be some method of doing that.
No, I think the problem is right that lower error plus higher error equals higher error, and generally kind of any function that if you have some function and you throw in a low error thing and a higher error thing, you get a higher error thing out. So because the errors are just randomly generated, you're not going to be able to make them cancel in some way.
Okay.
Right. So one subtle technical point. So this is this X is encrypted under S, and here we're saying we encrypted under S2. Technically, you could just set S equals S2, right? So you could technically just encrypt the bits of X under S, and then you can have the bootstrapping key be the bits of S encrypted under S. And this makes things a lot easier because instead of having lots of keys, or having an entire chain of keys with a chain of bootstrapping keys, you can just have one key. So why, in the standard descriptions of bootstrapping, don't people do that? Basically, for weird technical reasons, you can't prove kind of a security reduction straight to the lattice assumptions. And so there's this kind of special term, it's called circular security. And depending on whether or not you're one of these cryptographers who's no, you have to have proofs, versus one of these cryptographers who's yeah, whatever, it's fine, dog. It's your choice whether or not to trust circular security. A lot of people think it's fine.
I have a question. This S2 is also a public key, so the private key don't know. So you just have to use several public keys of the recipient for this to work.
Right.
What is the circuit depth of the decryption?
Good question, and I'm about to get to it in the next slide. So the main problem is that the multiplicative circuit depth of this decryption, it involves a modular reduction, and X mod P has a circuit depth of log X, which is bigger than log P, and this is higher than what FHE can support, right? So basically, one of the reasons why like nobody cares about the scheme that I just spent 10 minutes describing to you is because bootstrapping is not possible. So we're going to, in general, bootstrapping has a circuit depth which is logarithmic, and so the next parts of all of this are going to be kind of how do you make it, how do you adjust the scheme so that you actually can bootstrap. So we're going to skip over a few things. So Craig Gentry came up with some really clever tricks in 2009 involving subset sums and other things I don't understand to try to kind of get around this problem. So to try to reduce the circuit depth of bootstrapping to the point where you actually can bootstrap in a fairly simple FHE schemes. And Craig Gentry is great, and we love Craig Gentry, but and he's going to come back in the story. He is the one that created, or one of the people who created the matrix FHE protocol. But we're going to go straight to Zvika Barkirski and Vinod Vaikuntanathan's work in 2011, which is kind of the first scheme that really kind of managed to get around this problem, right? So the schemes that I'm going to show out from here on, they don't depend on approximate GCD. They depend on a slightly different but kind of similar seeming assumption, which is this learning with errors assumption, right? And the learning of errors assumption basically says that if you have a system of equations, if you have this kind of system of equations, you have a bunch of variables, you have a bunch of equations, normally you can solve them using Gaussian elimination, and it's fairly easy. But if you just have approximate equations, so you have a whole bunch of equations, and even if the system is really overspecified, that have a small additive error, then finding any of the variables becomes very hard, right? So solving systems of linear equations where the outputs have errors in them is something which is hard, and is something which as far as we know, is quantum hard. So these mechanisms also reduce to hardness of lattices and the shortest vector problem, and all of these other kind of problems that are fairly well studied in mathematics. So basically, the schemes that I'm going to get into from here on, they're not going to depend on approximate GCDs. They're going to depend on hardness of solving approximate systems of linear equations. So let's get to BV 2011. So the key is going to be a vector. It's going to be a vector of numbers, S1, S2 to Sn. And the ciphertext is going to be a vector A that satisfies the property that A dot product S is a message plus an even error. And this is all going to be done modulo some odd Q. Q doesn't have to be prime, but it has to be odd. So basically, what you generate an A such that A1S1 plus A2S2 plus dot dot ANSM equals M plus 2 times your error. So the connection between this and the learning with errors problem is basically that you can think of each of these ciphertexts as being an equation in your secret key, right? Your secret key is like S1, S2, S3, S4. The coefficients in the equation are going to be the A, and the output is going to be basically some small number, and it's 0 or 1 depending on what your message is, plus some error, and that error basically kind of perturbs the values, and that makes it hard to extract S. So your ciphertext is just, if you're kind of comfortable thinking in terms of vectors and dot products, it's just A such that A dot product S equals a message plus 2 times an error, or you can think of it as this linear equation. One optimization is that you can set the first number in your secret key to 1, and that just makes it very easy to construct these A's. Basically, you just generate all your other A's randomly, and then you set your SA1 to kind of compensate for whatever the rest of the dot product gives. And so whatever the rest dot product gives, you construct A1 to be kind of the minus of that, and then the minus of that plus S1 kind of adds up together with this, and then you get your your 0, and if you set a1 to kind of subtract another m plus 2e, then, or rather add another m plus 2e, then this whole dot product just becomes m plus 2e, right? So constructing vectors that satisfy this equation is very easy. So as I mentioned, an alternative interpretation of this vector interpretation is that a ciphertext is a noisy equation where the variables are your secret key. Addition is easy, right? So addition, basically, if you have AL such that AL.S equals 1 m plus 2e, and then AR such that AR.S equals another m plus 2e, then dot products are additive, and so AL plus AR.S is just going to be the sum of your messages plus the sum of your errors. And the way that you decrypt, obviously, is just you actually compute a.s and you take the last bit. And so you can decrypt the addition. And if you decrypt the addition, you get twice the even error. And then you have the kind of the sum, or rather the XOR of your two messages again, right? So addition here is simple. Multiplication is harder, right? So the problem here is that in the scheme I showed you before, you're just operating with single numbers, and single numbers can be added and multiplied. Here you're operating over vectors, and vectors can't just be multiplied with each other. Well, they kind of can, right? So you have this kind of notion of an exterior product, right? So basically, you have kind of this concept of an exterior product where a vector multiplied by another vector is just a big vector that contains all of the products of the elements, right? So if you imagine AL is a vector with 10 elements, AR is a vector of 10 elements, the exterior product is going to be this vector of 100 elements. It's like the first times the first, plus the first times the second, plus the first times the third, all the way up to the first times the 10th. Then you have the second times the first, all the way blah, 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 and then the 10th times the 10th. Now, you have this nice kind of algebraic identity that basically says AL exterior product AR dot producted with S exterior product S equals this dot product multiplied by this dot product, right? And so remember that AL is one ciphertext, AR is one ciphertext, and the product of the decryptions, so M1 times M2 is just going to be this dot product times this dot product. And so because of this algebraic identity, that equals the same thing as AL exterior product AR dot producted with S exterior product S. So if you take two ciphertexts and you just exterior product them, so basically you just turn them into this big vector that contains all of their all possible products of their elements, then that becomes a valid ciphertext of M1 times M2 under the key S times S, right? So you can multiply, but the length of your secret key grows quadratically. And so the challenge is you need to have a way of going back to linear. So to go back to linear, what we're going to do is we're going to have this procedure that we call relinearization, right? So the procedure for relinearization, it feels a bit like bootstrapping, like basically because what you do is you have kind of encryptions of S under your new key, and then you just evaluate things under your new key. So it's kind of similar to that, but it's doing something slightly different, right? So relinearization does not solve the error problem. It just solves the problem of taking a ciphertext under the key S times S or S exterior product S and turning it into an encryption under S. So the relinearization key is going to contain kind of encryptions of SI, SJ times 2 to the D. So it's going to contain basically SI, SJ for all I and J, so all elements of S exterior product S. And not just those elements, it's also going to contain those elements times 2, those elements times 4, those elements times 8, and so on and so forth going up, pretty much all the way up until for every power of D that's smaller than your modulus. And so what this lets us do is it lets us compute an encryption of the dot product of AL exterior product AR with S exterior product S as a linear combination of SI, SJ 2 to the D. Right, so if you imagine this expression, like just as we did in bootstrapping, we're not going to kind of evaluate it in a clear because well, you don't want the person executing the circuit to be able to figure out the output in the clear. So instead, we're going to evaluate it homomorphically under either some new key, or if you're willing to assume circular security, you can provide it under S if these encryptions are under S, right? So we're going to evaluate this whole thing homomorphically just as a linear combination of all of these powers, right? So for example, if you have AL as kind of 1, 2, and then AR as 3, 4, and so AL exterior AR is going to be 3, 4, 6, 8, right? So this is 1 times 3, 4 is 1 times 4, 6 is 2 times 3, 8 is 2 times 4. Then to evaluate AL exterior, the dot product of AL exterior AR with S exterior X, basically what you're going to do is you're going to say, well, you're going to have 3 multiplied by S1, S1, 4 multiplied by S1, S2, 6 multiplied by S2, S1, and then 8 multiplied by S2, S2. And then to avoid having to multiply ciphertext, because multiplying ciphertext like makes the error blow up, you have these powers of 2, and so the multiplication you can just express as a linear combination of these powers, right? So to express 3 times S1, S1, you're going to take this encryption of S1, S1 times 2 to the 0, plus the encryption of S1, S1 times 2 to the 1. And so this gives us S1, S1 times 3 encrypted under your new key. Then for 4, you just have S1, S. So here 4 is the second element in AL exterior AR, and so we're going to multiply it with the second element of S exterior X, which is S1, S2. So we'll use the encryption of S1, S2 times 2 squared. Then for 6, 6 is 2 to the 1 plus 2 to the 2. And so we're going to add the encryption of S2, S1 times 2 to the 1 with the encryption of S2, S1 times 2 to the 2. And then here we're going to add the encryption of S2, S2 times 2 to the 3. And so you basically, if you add all these encryptions, then you have a vector which is the encryption of, or rather a vector which kind of, if you were to dot product it with your key, it would give you S1, S1 to the 0, plus S1, S1 to the 1, plus blah, blah, plus some error, because each of these terms are going to have some error added to them. And so you're going to just add all of this error, and you have these set of terms. And this is going to give you 3 times S1, S1, 4 times S1, S2, 6 times S2, S1, 8 times S2, S2, which is the same thing as this term here, right? So basically what we've done is we've created this this sum of a bunch of these ciphertexts such that if you were to decrypt it, so if you were to dot product it with the new key, then you would actually get a value which equals to the evaluation of this plus some more error. And so if you were to evaluate it, then you were to cancel the error out, then because this gives you M1, M2 plus some error, M1, M2 plus some error cancel out the error, you would get M1, M2. So this both kind of preserves the message, and because it's an addition of a bunch of linear size ciphertexts, the ciphertext size and the key size also go back to linear. So I'll stop again and I'll kind of wait for questions, because real linearization is also not very intuitive.
Wow, this is super cool. One of the questions I have is, you mentioned that this helps reducing the size of the key, but not helping with the error.
Correct.
Why does it not help with the error?
It does not help with the error, basically because this expression itself, right, it's going to evaluate to this multiplied by this. And AL is equal to M plus 2E, AR is equal to M plus 2E. And so the product of those things is going to contain a term that has 4E squared. And so this thing evaluates to 4E squared. And so this thing evaluates to 4E squared. And so here you have 4E squared plus some more error that comes from a logarithmic number of these, right? So the error still blows up from being a multiple of E to being a multiple of E squared.
Mm-hmm.
Yeah. Now, there is another magic trick to make the air blow up less quickly, and I'll get to this after. But first, I'll kind of wait for questions about this scheme.
What does it mean to encrypt SISJ to the D if we
yes,
about encryption stuff?
This is, yes, very good question. I was about to actually answer this myself. So the encryption scheme as I provided, right, it can only encrypt 0 and 1 because it has some even error, right? And so you might ask, well, what does it mean to encrypt this thing, which is obviously going to be much bigger than 0 and 1? And so the answer basically is that the encryption in quotes of SISJ to the D is going to be a vector A, such that if you were to dot product it with the key, you would get SISJ times 2 to the D plus some even error, right? So you cannot actually extract SISJ to the D from the ciphertext because there's the error, and the error is just going to kind of wash away everything except for, well, it's going to wash away everything except for the really high bits and the low bit, but it's going to wash away some bits in the middle. But so it is basically a vector where if you dot product that vector with the key, then you get SISJ to the D plus even error. And so the reason why this is still useful is because if you add up these ciphertexts, then you still get AL times AR or AL exterior ER dot producted with S exterior X plus a whole bunch of even errors. But these even errors just kind of add together with the even errors that were already inside of here. And so whoever ends up kind of ultimately decrypting this ciphertext would still, like, the errors are all even, and so they'll be able to just take them
out. Okay, I got it. So it's just kind of not encrypted properly, like parts of the final ciphertext that you cleverly adapt.
Right. Okay. So here is the magic trick to make your error blow up less quickly. So first, kind of a fun fact, right? So we can switch ciphertexts between kind of what you can think of as being two perspectives, right? So one perspective is your ciphertext is A, and A dot producted S equals M plus 2E, where M is either 0 or 1. Now, if you just kind of modular divide A by 2, right? So this is all mod Q. Then A divided by modular divided by 2 dot producted with S gives you M becomes M over 2 and 2E becomes E, right? And so your even error, your small even error becomes a small error that doesn't have to be even. And M over 2, so 0 divided by 2 is 0, and 1 divided by 2 is ceiling of Q of half your modulus, right? So if your modulus is, say, 999, then 1 divided by 2 is going to be 500, right? Because 500 times 2 is 1,000, which modulo 999 reduces to 1. And so you can basically take a ciphertext that's of this form, and then you divide your A by 2, and then you convert it into a ciphertext that has this format where instead of your message being in the lowest bit, your message becomes kind of in the high order bits. Now, this perspective is better for multiplication, because if your message is in low order bits, then when you multiply your two messages together, your message is still kind of preserved, right? Your message is in the kind of the field of two elements, or, and I guess you can't divide, so the ring of two elements might be a little more precise, right? Like basically, if your message is in the low order bits, then everything that happens with the error kind of happens on top of the message, and the message just kind of flies under, and it doesn't get affected. But in this perspective, the message is at the top, and so everything interferes with it. So in this perspective, you can't multiply. But this perspective has a key advantage, which is that it makes the noise less structured, right? So here, the noise has to be even. Here, the message just becomes small. And so by cleverly switching between these perspectives, you can, without having the secret key, change the modulus of a ciphertext. So here's what we do, right? We start off with A such that A dot product S equals your 0 or 1 plus 2 times the error. Then you do a perspective switch. And so you have an A prime, which is A modular divided by 2, which is equal to small error plus either 0 or half your modulus. Now, what we're going to do is we're going to switch it from mod Q to mod P, right? And so what we're going to do is we're going to take this ciphertext, we're going to take the A prime, and we're going to multiply it by P, and then we're going to integer divided by Q. And so if you do this, then what you're going to get is you're going to get a value which, if you then multiply it by S, so you do rescale A, but you do not rescale S, right? So this is a bit kind of important. So if you the rescaled A prime gives you basically, well, if you dot product it with the same thing, then the output is going to be rescaled, and so 0 becomes 0. Ceiling of Q over 2 becomes roughly ceiling of P over 2. Small error becomes small error, except the error itself also gets kind of downscaled, right? So it gets downscaled from being something times Q, some small fraction times Q, to being the same small fraction times P. And so the actual magnitude of the error kind of goes down. And then when you basically do a reverse perspective switch, and so you go from this perspective where it's either 0 or ceiling of P over 2 to this perspective, you double this, and then it becomes either 0 or 1 plus 2 times the error. Now, this operation...
I didn't understand the previous step about...
Okay.
Yes, why is there...
Why this times P divided by Q trick works.
Yeah, why it gives you the one on the right? Why is the message now 0 P over 2? That's not obvious.
Right. Basically, so if you just think of this as being just a multiplication, then if it was an encryption of 0, then it's just going to give you a multiple of Q. And if it was an encryption of 1, then this gives you a multiple of Q plus half of Q, right? And so if you multiply this by P over Q, then multiples of Q turn into multiples of P, and multiples of kind of half multiples of Q turn into half multiples of P. So I guess like one example is that if you imagine, say, Q is 5,000 and P is 1,000, then if A prime dot S is, or let's say Q is 10,000, P is 1,000, just for simplicity, then if A prime dot S here was, say, 50,000, or let's say 50,000 plus a bit of an error, then if you go down from Q to multiply by P over Q, so you basically P is 1,000, Q is 10,000, so you divide it by 10, so your 50,000 just becomes 5,000, and 5,000 modulo 1,000 is still a 0. But if you instead had, say, 55,000, then 55,000 times P over Q is going to be 5,500, and so modulo 1,000 is going to be 500. And the error that gets introduced by kind of the floor division not being perfect is still a small error, so it just kind of mixes together with the small error that already exists.
So this should really say E prime as opposed to E, right? It's a different
correct. Error. Yes, sorry, that's correct. This should be E prime.
And even the contribution from E, that's also going to change.
Right. So, and to just kind of go back to this example, right? So let's say your A prime dot S was like as an integer dot product equal to, let's say instead of 55,000, it was equal to 55,030. So your error is 30. Then if you multiply by P over Q, 55,030 turns into 5,503. And so modulo 1,000, it's going to be 503. 500 is P over 2. And so your new error, instead of, it was 30 before, and now your new error is 3.
So basically the ratio between the error and the modulus size remains the same.
Correct. And I'll explain why it seems like you're not accomplishing anything because the error ratio is the same, but you're actually accomplishing something really important, which I'll get into in the next slide. So right now, right? I guess, are people satisfied that if you have a ciphertext whose error gets bigger, you can turn it into a ciphertext whose error as a number is bounded by some constant, but it's just a modulus that keeps being reduced, right? So this is kind of the lesson here.
Yeah.
Okay. So here is why we switch, right? So there's two reasons to switch, actually. So the first reason to switch is this makes bootstrapping actually practical, right? So bootstrapping involves basically computing this dot product a.s mod q, and computing this dot product a.s mod q has a circuit depth of log q, and by reducing the modulus, what we can do is we can basically turn something which to decrypt requires a circuit depth of log q to something that has a circuit depth of log p. And p here is like can be very small, right? Once you do the modulus switch, you don't have to actually do any more computation, so p can be a pretty small constant. And so this basically means that the circuit depth of bootstrapping becomes a constant. And so you can just increase q to as much as you need in order to make the bootstrapping procedure actually possible.
Cool.
Yeah. So in the bootstrapping key, basically the way that we do it, so bootstrapping is just kind of computing this dot product mod p, or kind of as a circuit. And so to make this computable, you basically you're going to provide SI times 2 to the D values in binary representation, right? So for every SI times 2 to the D, you basically, and this is modulo p, then you provide a binary representation of this, and so you have n log p numbers in binary representation. So for every one of these terms, you have your Sn. Basically, to compute Sn, you take for every one bit that's in An, because you have An in the clear, you multiply that by the corresponding kind of bit representation of kind of the power of Sn, and so you just have a bunch of these numbers. And these are numbers in binary representation, right? So they're not single ciphertext, they're log p ciphertexts. And then you just add a whole bunch of these numbers together. And then to take modulo, if you, like, the best choice of p is going to be 2 to the power of n minus 1. And that makes modulo really easy because you just make your addition circuits wrap around. So how do we implement, right? So how do we implement these addition circuits, right? So basically, the addition circuit is just going to be, you have these n log p numbers, and you just have to add together these n log p numbers, right? And then the modulo, basically, your addition circuits, instead of carrying onto kind of even higher bits, like every time you carry past the size of p, you just kind of wrap around, right? And then that just gives you modulo 2n minus 1 for free, right? So like if your modulus is 1023, then your bits are 128, 256, 512, then 1024 is equal to 1, so you just kind of wrap that around to 1, so moduloing is really easy. So your setting is you just have to add together a whole bunch of numbers, right? And the first step is that you can reduce 3 numbers to 2 numbers, so you can have a kind of 3 to 2 adder that has multiplicative depth 1, right? So, and the way that this works is basically that every bit of p is going to be just the XOR of the corresponding bits of A and B and C. And every bit of q is going to be kind of the 2 of 3 functions of A and B and C, right? So this is 0 if A plus B plus C is 0 or 1, and 1 if A plus B plus C is 2 or 3. And you can think of this as being carry digits, right? And the q, you also kind of multiply it by 2, which basically means you just kind of left shift q by 1, right? So the reason why this works is basically because every bit in A and B and C gets represented inside of p, but then in the specific case where you have kind of 2 bits that are turned on to 1, then inside of p they get turned into 0, but but you flip the corresponding q from a 0 to a 1, and then the q gets kind of moved to the left by 1, and so that multiplies it by 2. And so basically kind of every individual bit in A, B, or C gets kind of correctly represented in P plus Q, right? So this is a kind of 3 to 2 adder, and this has multiplicative depth 1. Adding two numbers x plus y does require logarithmic multiplicative depth, right? So when you if you going from n numbers to 2 numbers, that requires the multiplicative depth, which is basically logarithmic in n. So logarithmic in the number of numbers, and we don't care about the size. But then adding the last two does require multiplicative depth log x plus y. And here x and y are mod p, so we're basically saying log p, or log of the number of digits of p, right? So if p is 1023, then p has 10 digits. The log of 10 is going to be 4, and so your multiplicative depth is just going to be 4. Now, the reason why adding circuits have this non-logarithmic multiplicative depth is basically because you have to worry about kind of threading the carry bits through the number. And I mean, in the code that I'll link to later, I have algorithms for doing this. So in general, computing a linear combination of size n log p is going to take size. So first of all, you have these n numbers, and second, you have this kind of the n numbers together. They're gonna the sum is going to be a size n log p, and so it's kind of log of n log p, and so this becomes log of log n plus log p. Here you have another log p, and so the total kind of O is going to be a kind of log n plus log p, and you can pretty easily just set q to be high enough that this is less than log q, and so you can basically you can implement the decryption circuit, and so you can bootstrap. So here's optimization number 2, right? So I mentioned back when we were over here, right, that there's two tricks to overcome overflow, where one is bootstrapping and the other is clever tricks to make your multiplication only increase your error by a constant factor. So this is the clever tricks that I'm going to talk about, right? So basically, imagine if instead of just doing a modular switch before bootstrapping, we do a modular switch after every multiplication, right? So if you don't do this, right? So if you imagine a circuit that has some multiplicative depth, then your error is going to square every time you do a multiplication, right? So if you imagine your first ciphertext, let's say the modulus is 10 to the 16 minus 1, and your ciphertext has error 10 squared. If you square it, the error is going to be 10 to the 4. Actually, it'll be a 10 to the 4 times some constant, but we'll simplify and we'll say it's 10 to the 4. Then the third time you multiply, the error is 10 to the 8. Then the fourth time you multiply, the error is 10 to the 16, and then the error kind of overwhelms the ciphertext, and then here decryption starts failing. So if you just do this kind of fully homomorphic or just partially homomorphic encryption naively, then after a logarithmic multiplication depth, you're screwed. Now, what happens if you do modulus reduction, right? So you have x, which has an error of 10 squared, modulo 10 to the 16 minus 1. Then you multiply it, and so you have x squared with an error of 10 to the 4. Now you perform a reduction. And so here you have x error 10 to the 4 modulus 10 to the 16 minus 1. We're going to basically cut the modulus by a factor of 100. And so your error gets cut from 10 to the 4 to 10 squared, and your modulus gets cut from 10 to the 16 to 10 to the 14. And so now you have this term over here. And then you can, over here, or you have this term over here. And now if you square this again, right, then your x squared goes up to x to the 4. Your error of 10 squared goes back up to being an error of 10 to the 4. Your modulus is the same. Then you reduce it again. And now your error goes down to 10 squared. Your modulus kind of hops down again. Then you square it again. The error goes up from 10 squared to 10 to the 4. And then you just reduce the modulus again. And so notice that instead of the error squaring every time, basically we have the modulus just kind of very nicely, orderly, just stepping down by a constant factor every time, right? So the clever trick here is basically that when you multiply the ciphertexts, the errors get multiplied. And so if you just make sure that the errors as numbers stay small, then squaring the error is always just going to be a constant factor multiplication. And so instead of having a logarithmic number of steps, you can have a linear number of steps. And so your multiplicative depth goes up from log q to log q. Pause for questions again.
I didn't completely follow everything. So it's multiplicative depth of what? Don't we want to decrease the multiplicative depth?
Oh, sorry. By multiplicative depth, I mean the maximum multiplicative depth that you can support, right? So if you notice, like the example at the top and the example at the bottom, here your error blows up to the point where it overwhelms the modulus after 3 multiplications, right? Because each time you're squaring. Here, we're keeping the error under control, right? The error is just always 10 to the 4, down to 10 squared, up to 10 to the 4, down to 10 squared, up to 10 to the 4, down to 10 squared, except every time the modulus just steps down by a constant factor of 10 squared. And so here, instead of doing 3 steps, you can do 8 steps, right? So here you can do log q steps, here you can do log q steps.
And both optimizations are kind of unlocked by this context switch idea.
Right. So both the bootstrapping and this technique that lets you basically not need bootstrapping half the time are unlocked by the modulus switch.
Cool.
Okay. So now we move on to what this presentation was supposed to be about, which is matrix FHE. So the problem that matrix FHE solves is basically, can we try to find something that's kind of more natural and more efficient than relinearization, right? So relinearization is expensive, basically because relinearization requires you to just add this really huge number of ciphertexts. And if you imagine a large modulus, you're talking about hundreds of ciphertexts for each element. So can we try to make something that's kind of somewhat nicer? And can we also try to create a protocol that's somewhat simpler, where adding and multiplying ciphertexts actually is done by adding and multiplying elements in some kind of naturally reasonable array. So matrices, yay. So here is kind of the context, right? So to encrypt to encrypt 0 with a secret key, what we're going to do is we're going to have come up with a matrix A such that the secret key multiplied by the matrix is an error. And to encrypt 1, we're going to have a matrix A such that a secret key multiplied by the A gives the secret key plus an error, right? So basically what we're doing is we're kind of hiding an approximate eigenvector where here where the eigenvalue, if it's 0, the eigenvalue is 0, and if it's 1, the eigenvalue is 1. And if you really want, you can potentially encrypt other values as long as the eigenvalue kind of becomes the place where the plaintext gets hidden. And it's only an approximate eigenvalue, and so you can't extract it using kind of the standard techniques for the standard, because learning with errors makes it hard. So addition is easy, right? Basically, addition, if you just add together 2 matrices, then, so if you add together a matrix such that SA equals something with a matrix where SA equals something else, then S of AL plus AR is just going to be basically whatever the value is for the first one plus whatever the value is for the second one, right? So S times AL, or decrypt of AL plus AR becomes decrypt of AL plus decrypt of AR, which is going to be your left message times S plus your left error plus your right message times S plus your right error. And so you have the sum of your messages times S plus the sum of the errors, right? It's basically kind of the same thing that we had before. Except here, because instead of dealing with vectors, we're dealing with matrices, and matrices, yay, can actually be multiplied, then the decryption of the multiplication of the matrices is going to be S multiplied by AL times ER. And remember, you can think of matrices as being linear maps, and so you're going to kind of pass S through AL, and then you're going to pass S through AR. And so the eigenvalues get producted as well. And so you can kind of show that this kind of expands out. So you have first S passing through AL, then you multiply that by AR. And so S times AL is going to be a kind of MLS plus plus EL as before, right? So here, like S times A is going to be whatever your message is multiplied by S, either 1 or 0, plus your error. Except here we still have to multiply it by AR. So you have MLS times AR, then you have EL times AR. And so here, multiplying by AR basically means your MLS is going to turn into, well, ML MRS, because AR times S by itself is going to give you kind of MRS, right? And so if S times AR gives you MRS, then ML times S times AR is going to give you ML MRS. So here, kind of the decryption of the product is going to give you kind of the product of the messages here. And then over here, you have is the two error terms, right? So one of the error terms is going to be the left error multiplied by AR. And then here you have the right error multiplied by AR multiplied by the left message. So you can add, you can multiply, but there's a problem, right? And the problem is that the error is not just being multiplied by the other error. You're not just having like EL times AR. Instead, your error gets multiplied by the magnitude of the matrix elements. So if you start with matrices that have a fairly small magnitude, then every time you do a multiplication, the magnitude of your matrix elements just keeps on doubling. And so once again, you're limited to your depth being kind of log Q. By the way, just kind of one other reason why this matrix approach is nice. Basically, we don't, from here on, we don't actually care about the moduluses being odd. We don't care about them being prime. We don't care about moduluses having any kind of properties. And so to make the math easy, we're just going to set the moduluses to equal some power 2 to the k, and that makes them kind of math really easy. And it makes bootstrapping really easy as well, because you could just kind of forget the higher order bits. So the problem is, right, that you have this kind of EL multiplied by AR, and these AR values themselves are kind of get big, and they get bigger every time you multiply. And so how do you stop the error from just blowing up? So the fix to this problem is you have this kind of really strange and clever bit splitting trick. And the bit splitting trick basically says that if we treat x as being a vector, then we're going to define these two functions. One is called powers of 2, the other is called bitify, where powers of 2 basically says for every element in x, you just kind of concatenate the powers of 2 of x, and then bitify of x just turns it into a bit representation. Then you have this identity that the dot product of powers of 2 of x together with the bitify of y equals to the dot product of x of y. And to kind of visually show this, I have an example, right? So if you have x is 1, 2, 3, and then y is 6, 5, 4, then powers of 2 of x of 1 turns into 1, 2, 4, 2 times into 2 times 1, 2, 4, so 2, 4, 8, and then 3 turns into 3, 6, 12. And then y turns into its bit representation, so 6 is 1, 1, 0, 5 is 1, 0, 1, 4 is 1, 0, 0. And the dot product here, well, here it's 1 times 6. And then here we're basically kind of doing powers times bit representations. And so you have 2 times 1 and then 4 times 1. So this adds up to being 6. Then over here, 2 times 5. And you basically, the 5 turns into 1, 0, 1. And so you add 2 times 1. And then here you add 2 times 4 times 1 to kind of compensate for this 1 having a higher place value. And so 2 times 1 plus 8 times 1 is 10, which is 2 times 5. And then 3 times 4 is 12. And so 3 times, well, here, 4, you just have like a 1 here, and then the 1 gets multiplied by 3 times 4, and so you have 12. Right? So I guess also pausing and just kind of stare at this and just kind of verify for yourselves that this works. Right? So basically, powers kind of converting x into powers of 2 and converting y into a bit representation is a dot product preserving operation.
It kind of feels a little bit like the relinearization trick.
Exactly. Yes. It's very similar, except this is kind of just explicitly representing relinearization using vector math. It's exactly the same sort of stuff. So the bit splitting technique also applies to matrices because matrix math is basically just batched vector math, right? And so powers of 2 of s times bit of phi of a equals equals s times a. Actually, this should be a dot. This should be just actual matrix multiplication. And so what we're going to do is we're going to basically do, instead of doing AL times AR, we're going to do AL times bit of phi of AR, right? And we're going to set our ciphertext, instead of being n times n, we're going to set them as being kind of n times n log p. Basically, the idea is that whatever is on the left side, we're going to kind of set it as being permanently in this kind of powers of 2 representation. And so bit of phi is going to give us an n log p times n log p of matrix, and so kind of the dimensions match up. But instead of multiplying AL times AR, we're going to multiply AL times bit of phi of AR. And the reason why we do this is basically because if you notice here, you have these two terms, these two error terms. One has ERAR and one has ELAR. And so if AR elements are always going to be 0 and 1, then here you just have EL, and then here you just have ER multiplied by the message, which is just going to be 0 or 1. And so the error blowup is small, right? The error blowup is just going to be adding a whole bunch of these terms that were proportional to the original error. So I'll admit it's the thing that's kind of difficult to see is why AL times bit of phi AR is still eigenvector preserving the same way that AL times AR was eigenvector preserving. Again, basically, how do I describe this? Like the idea, the kind of intuitive idea, right, is that these ALs are kind of permanently in this powers of 2 form, and then these ARs are going to be bitified, and so their dot product is going to be the same as it was if you just had a kind of regular AL together with just a regular AR. And so the eigenvector here, instead of, well, here it's not kind of fully an eigenvector. Instead of being S, instead of turning S to S, it's actually going to turn S into powers of 2 of S, but kind of this works, and you can kind of, you can also just experimentally verify that it works, right? And the benefit is that, as I mentioned, instead of the error blowup multiplied by big AR values, you just guarantee that these AR values are always 0 and 1, and so the error blowup is smaller. Right. By the way, if anyone, I have code here, so if anyone and the code is actually not long, so the homomorphic encryption here is about 300 lines of Python. This is under 200 lines of Python. So if you want to kind of see for yourself, if you want to kind of play around with matrices for yourself and kind of verify things for yourself, I highly recommend looking through the code as well. So optimizations, right? So there's a bunch of ways to optimize this. So first of all, you might notice that one of the really interesting problems or properties of matrix FHE is that the error growth is asymmetric. So here you're multiplying by AR, and here you have just EL. Here you have ER being multiplied by a message, and you have this interesting property that if you have a ciphertext on the right that has a higher error, then the error actually barely increases at all. Right, and so what this basically means is that if, whereas in tensor FHE, you might, you don't really have this property, the errors kind of just multiply. Here, if you want to perform some kind of operation, then it actually makes sense to perform that operation kind of asymmetrically. So say if you want to do a bunch of additions, then you just kind of fold them all into the same sum, one after the other. The error bounds criterion becomes kind of more complicated. So it's not just max multiplicative depth. It's not just max polynomial degree. It becomes this weird complicated thing. other optimizations, so you can decompose, so you don't need to do things in base 2, or you don't need to decompose into kind of binary n powers of 2. You can also do this in base 3 or base 4 or base 16, and this potentially lets the error kind of increase less slowly. You can pack multiple bits into a ciphertext, and you can do kind of addition and multiplication on a lot of bits at the same time. There's also this thing called ring LWE, where basically instead of just thinking about kind of a whole bunch of independent equations, you can represent those equations as being an equation in a polynomial ring. And I don't really have time to get into this, but this also lets you kind of decrease key sizes a lot. So this is still kind of basically how a kind of modern fully homomorphic encryption schemes work, except there's this kind of whole suite of optimizations that people have been slowly coming up with. So the main reason why there is a big overhead is basically because the ciphertexts are matrices, right? And in order to satisfy these LWE assumptions, the ciphertexts have to have a pretty substantial length. And so you can think of these matrices as being something like 100 matrices of size 100 by 100 or whatever. And then here we're going to store them in powers of 2, and we're going to bitify them. And so the 100 potentially blows up into being 10,000, at least temporarily. And so matrix multiplication becomes this really big kind of multiplication procedure. And if you want to be able to process circuits of substantial size, then these numbers have to have a fairly substantial bit length. So we're potentially talking over 100 potentially. So there's a bunch of factors that do end up kind of conspiring to make it fairly or to make this kind of fairly inherent large blow up in circuit sizes. And this is the reason why this is all kind of less large and less clean than things like elliptic curve cryptography, for example. But it is kind of increasingly getting to the point where, for at least small computations, it is completely viable, and you can do kind of individual computational steps on the order of milliseconds. So there you go.
Thank you. That was really cool. Thanks for the presentation. I have a question of do you know what is considered the state of the art today? Like there is all these different libraries out there, the FHE and all these kind of things. So what method and is considered the best today?
Right. There's definitely a bunch of libraries, like HElib is one of them, and there's some others with different names. So there's a survey by Zvika Burkursky, the inventor of the 2011 protocol. So let's see if I can look this up right now. Here you have fundamentals of fully homomorphic encryption. And so it's basically just search fundamentals of fully homomorphic encryption with Zvika Burkursky, and then what you get, it's from 2018, and it basically describes something similar to the matrix FHE protocol. So the state of the art is definitely you start from either the tensor approach, so the exterior product approach, or the matrix approach. They have different pros and cons, and then you just apply a whole bunch of optimizations. Ring LWE is one of them. Another one is this various schemes for being able to kind of stuff a whole bunch of ciphertexts into this, or a whole bunch of messages into the same ciphertext. So like one of the ways that you can do this is you can imagine here, instead of having a ciphertext where A just satisfies A dot product equals one message, you might say A dot product S one message, and A dot product T satisfies another message, and then you can do kind of SIMD operations. So you can, if you add and multiply, that kind of adds and multiplies all the plain text simultaneously. And then you can do kind of rotations, you can do kind of permutations. And so there's this kind of growing body of clever tricks, the same way that the zero knowledge proof space has a growing body of clever tricks that try to compensate for the inherent inefficiencies. So that's where we're basically at right now. We're at kind of just taking this base and incrementally building upon it.
Awesome, thanks. I sent a link to the report that you referred to in the Telegram channel.
Great.
I just have a quick
you
question.
can also look up.
Oh, sorry, like finish this one first. It's a
No, I was just going to mention that you can also look up BV 2011. There's also another protocol, BV 2012, which avoids the need to do modulo switching completely, like basically by kind of pretending that the ciphertexts are fractional, but still representing them as integers. So you're just kind of feel free to look up the papers for all of these as well, and hopefully they'll be more understandable after this.
All right, thanks.
But go ahead.
Yeah, this is like just coming back to your last thing about the switching into AL and AR matrices. So where yes. Okay, so you can do this multiplication. So how in the next step, right? You do it using the Spitify. Isn't that actually exactly? I haven't quite understood why you're not doing exactly the same operation and just computing it in a different way.
Right. So basically, the idea here is that Bitify is guaranteed to always contain zeros and ones, right? I think I might have a good intuitive answer. So the intuitive answer is, so first of all, like powers of 2 or kind of power of 2 reduction and Bitify are kind of opposites in some sense, right? So if you Bitify something, then you can multiply it by a matrix, which kind of converts it back into the pre-Bitified form. But if you take a matrix which is Bitified and multiply it by a matrix which is in this case not Bitified, then the multiplication itself, when you do kind of modulo, it's going to, and then you kind of unbitify. You're basically kind of, what this is, and you can think of it as being kind of an unbitified version of a bitified thing. And what happens is that the kind of inverse of bitifying that's kind of inherently baked into here, it has this property that if you apply it to things that are not bits, right? So a bitified matrix multiplied by another bitified matrix is not necessarily going to contain bits because matrix multiplication adds a whole bunch of bits together. Then you're still going to get a matrix, and you're still, because you have modular reduction, it's going to reduce to modulo whatever your modulus is, and then so basically the modular reduction just kind of magically makes the higher order terms go away. And because you're only doing the matrix multiplication while the matrices are bitified, means that the process of matrix multiplication never multiplies any particular value by more than the width of the matrix. And so the error only gets multiplied by a small amount, right? So it's actually not the same operation. It's a different operation, but which is still guaranteed to have kind of the same consequences, specifically with respect to multiplying by like basically things that of the format of.
So I actually just noticed that I don't even know what this multiplication here means, because like, so in the previous operation, okay, so we have like Bitify has blown up a vector into, okay, an n times log p vector, right? So what are these AR and AL objects here? Are they tensors or are they still two-dimensional matrices? How many
these are all matrices, right? So the way to intuitively think of this is, okay, so here's one way to intuitively think of this, right? So think of AL as being a bitified matrix multiplied. So AR has size n log p times n log p, right? Bitify AR is a big square. AL has size kind of small times big. It's n times n log p. And think of AL as being bitified AL multiplied by the matrix that is the inverse of bitification, right? So imagine you have like the inverse bitify matrix multiplied by bitify AL multiplied by bitify AR. and then you're going to take bitify AL and bitify AR, then you multiply them together, and then to actually see what this means, you have your kind of inverse bitification matrix multiplied by the product of the bitifis. So, right. So basically, you have these kind of matrices that have the property that if you multiply them by powers of 2 of S, then you get powers of 2 of S. And so here you have kind of already squashed matrices, and so if you multiply them by S, you get powers of 2 of S. And then if you take AL and kind of expand it out and as a bitified thing, then the bitified things are they're both powers of 2 of S is an eigenvector basically. And so if you product together bitify AL with bitify AR, you get something where powers of 2 of S is also an eigenvector. And then if you kind of squash it back, then you get a ciphertext that's still kind of the same form.
Right. I think, yeah, I mean,
if he wants to kind of.
Yeah, I think I realized the parts that I don't understand yet. I guess I'll have to look at the source.
Right.
Yeah.
I'd recommend not even just looking at the source, but even just kind of opening up a Python console and kind of playing around with kind of bitify and multiplying by vectors and just kind of see what properties the ciphertext and the bitified ciphertext have with respect to multiplying by S and multiplying by powers of 2 of S.
Okay, all right. Okay, so now, here's the part I didn't understand. So there's no extra operation each time. Now, the whole time, we are computing with n times n log p matrices.
Yes.
Aha, I see. Okay, so we changed our protocol. This is not just like a modification of the multiplication itself.
Right. Right. So another way to think about this, I think this approach is just an optimization. Another way of thinking about this is you can make a less efficient but easier to understand protocol if your ciphertexts are n log p times n log p matrices. So imagine your ciphertexts are kind of bitify AL and bitify AR, right? So they are big matrices that contain only zeros and ones that have the property that powers of 2 of S is an eigenvector, right? So we agree that if you just multiply AL times bitify of AR, then powers of 2 is going to be of S is going to be an eigenvector of the product, right? But then what this operation does, basically, we want to preserve the invariance that your ciphertexts are just zeros and ones, right? After you multiply 2 matrices together, they're not necessarily zeros and ones. And so what we're going to do is we're going to basically kind of do an inverse bitify operation, so squash it. And because of this, squashing preserves the eigenvector. So basically, before it turns powers of S into powers of 2 of S into powers of 2 of S, after it just turns S into powers of 2 of S, you squash it, and then you bitify it again. And the squashing and the squashing and the expanding, it preserves the eigenvector, but it kind of forces the values in the ciphertext to just continue being zeros and ones.
Cool. And you mentioned like you can do operations in order of milliseconds. That's like sort of one bit, essentially, like a 1-bit operations, like something like
yes.
and more.
Right. I
have a question.
Yeah, I'm not sure. Oh yeah, go ahead.
First, thanks for a fantastic presentation. And the question is, you have talked so far only about multiplications of plain text and ciphertext, but do you think that any of this technique translates to some more complex functions, like polynomials of ciphertext, something like more naturally than just computing them operation by operation?
Yes, I mean, it's a good question. I think, so one of the challenges is, right, so first of all, this, this technique, it's theoretically compatible with ciphertexts being not just zeros and ones, but being arbitrary field elements. The problem is that because you have this ML-ERAR term, basically, if your messages are not zeros and ones, it makes the error blow up quickly, right? So you can get some, like you can potentially, instead of working in the ring modulo 2, you can work in like the ring modulo some small number, like maybe up to 100 or something. But working over things that are not bits, it just kind of seems intrinsically hard because multiplying by things that are not small numbers causes error to blow up very quickly. So
no, I mean,
you do pretty much, oh.
Sorry, I meant differently. Not no. Just kind of not field elements, but instead of like just multiplication, like I know multiple of 3 different elements, or I know some polynomial of 4 elements of small degree or something.
Right. So I mean, so the trivial way to do any of this, right, is that if you want, well, if you want to like there are mechanisms for, I think, multiplying a sorry. So if ML, if the individual ML kind of as bits, right, is just a 0 or 1, then multiplying by 3 doesn't really have anything, right? So if your messages are zeros and ones, then you pretty much have to do everything using binary circuits. And the nice thing with binary circuits is that, like, you can kind of, like, multiplication is just an addition of a kind of log n left shifted values, and so you can kind of do it. And I mentioned before in the optimization section, right, that you can potentially have a ciphertext which contains multiple plain text, and you can do shifts. And so you could do a kind of large parts of things like addition and multiplication circuits kind of operating over many bits simultaneously. But I guess in general, like operating over binary circuits is the kind of the most fundamental thing that this ends up allowing. There are definitely kind of optimizations where if you want to, like, so the main challenge here, right, is to prevent the error from blowing up. Your messages have to always be 0 and 1, but there are optimizations that have to do with kind of computing more complicated gates in a way that ensures that the output is still 0 and 1 without having to do as much work as if you just kind of did it naively with simple gates. So there's nothing kind of super mathematically elegant, but there are kind of these kind of bags of tricks that let you optimize a lot sometimes.
Okay, thank you.
One question I have is that people often say that functional encryption is related to FHE. Do you know how to go from FHE to functional encryption? Or how they're related?
Right. So functional encryption, in terms of the definition, basically it says instead of being able to go from enc of x to enc of f of x for arbitrary f, you can go from enc of x to just having f of x, but only for one specific f. So it's a kind of different and potentially more powerful primitive. In terms of how these functional encryption protocols work, I'll admit I haven't kind of fully figured this out yet. They're definitely considerably more complicated than FHE.
Okay. I mean, I guess one easy way, well, quote easy conceptually, is to go through obfuscation, bootstrap with FHE, and then go back down to functional encryption.
Right, exactly. But even, well, if obfuscation protocols often in practice end up being built on top of functional encryption. So.
Oh, okay.
That's yeah. And there's like a lot of different paths to try to get to obfuscation, and none of them kind of fully satisfy people yet, and they do end up having overhead. One really nice thing is that if you have an obfuscator that works for circuits of constant size, then you can turn that into an obfuscator that works for kind of arbitrary size. And the way that you do that is to obfuscate a big program. You first homomorphically encrypt the input, then you have the circuit itself provided in a homomorphically encrypted form. And so basically your function is going to be circuit evaluation. And so you're going to evaluate the encryption of X with the encryption of the circuit, and then you get an encrypted form of the output, and you generate a some like proof. So think of it as being a snark or something. But like you can make proofs that kind of play more nicely together with the homomorphic encryption scheme, so you have less blow up. So you basically, then what you do is you take your encryption of f of x, and you take your proof that you actually computed f and not some different function, and then you have a fixed sized program that checks the proof and then decrypts and if the proof is correct, and then you have your f of x out, right? So that way you can kind of obfuscate programs. So you create kind of an encrypted program that lets you go from f to f of x. But this still depends on a fixed size obfuscation.
So I think pretty much the exact same technique works for something called correlation intractability hashing. And I think the idea here is that you can have a provably secure fiat shamir as opposed to having a heuristically secure fiat shamir. And then if you have this hash function, which has this very special property on small circuits, then you can boost it to arbitrary circuits. And I think some of the lattices people managed to build a non-interactive zero-knowledge proof, which is secure in the standard model without using fiat shamir.
Mm-hmm.
I guess another question I have.
That's. Mm-hmm.
Go ahead. What were you going to say?
No, I was just gonna say that sounds right and interesting.
I mean, the other question I have is on performance. So, like, this one guy said that, roughly speaking, in a decade, like FHE was optimized by an order of magnitude every single year. And I was wondering if you think we've hit a wall, or like this is going to continue, because it's needed to continue for 4 or 5 years, and then help you. 4 or 5 years.
Right. Yeah, so I mean, I've kind of taken you through the journey of kind of the years of where homomorphic encryption was just getting kind of massively better with new discoveries every 2 years, right? So like over here you have only partial homomorphism, so bounded degree and bootstrapping is impossible. Then you have this really complicated scheme from Craig Gentry. Then you have this really clever trick that finally allows you to bootstrap for the first time, but the error blows out exponentially. Then suddenly, ta-da, the error only blows up linearly. And then, ta-da, now the complexity of doing a multiplication went down to a matrix multiplication. So here, we're seeing huge speed-ups. I think after these protocols, the speed-ups have definitely started slowing down. And I expect speed-ups to kind of continue slowing down over time. I don't know enough to be able to say honestly like what a reasonable lower bound would end up looking like. Like I think my instinct would say at this point that we'll probably expect to see more speedups from optimizations than we will from a kind of very fundamental changes to how ciphertext work. So kind of coming up with gadgets that let us operate on kind of many bits at the same time more effectively. But, I don't know.
Right.
Okay, do we have more questions?
I mean, one thing I'm kind of curious about is kind of the ultimate kind of cryptographic primitive for the long-term future, let's say when we have quantum computers. And it's kind of unfortunate that, from what I understand right now, like we can't really do snarks with lattices, and I was wondering if you think this is like a fundamental thing, or like we're gonna need try and lattices working in parallel.
Huh. So you can do bulletproofs with lattices, right? Because you can just use ciphertext the same way you use Pedersen commitments. As for, it's very possible that someone will come up with some lattice-based protocol for kind of zero knowledge proving. I don't know. And I think the reason why it seems fundamentally harder in the lattice world is because you have these errors, and so you can't really do things like equality tests as easily, right? Like, so like, for example, even one of the big kind of problems with, or challenges in lattice, like this style of cryptography, is, can you even come up with a zero testing key? And because of linearity, if you have a zero testing key, you can turn that into an equality testing key, and that would just immediately give you a multilinear map. And it turns out that all of the approaches that people have come up with for trying to zero test if some ciphertext equals to zero, using some key that allows you to do that without allowing you to decrypt everything else, like, it's inevitably leaks information that kind of breaks the security proof that shows that you can't extract everything else about the message. So yeah, we might end up coming up with something. I don't know. It definitely is possible that we'll end up needing both FHE and lattices in the long term, and that the two things just naturally specialize in different areas.
The zero testing is very interesting.
Yeah, I mean, it's one of like 10 things where if we had it, then we would just solve everything. So sad.
Thank you so much. This was really interesting.
Okay, well, thank you
Yep,
all for
thanks
listening.
very much.